All right, guys, oxidation reduction chemistry. Here's what we're going to do today. We're going to talk terminology. It's going to take us a couple slides. And then, guys, following that, you are going to learn to balance oxidation reduction reactions. Now, here's the thing. I started teaching AP chemistry in 2001. So this is what? Year 8, holy buckets, year 18 of teaching AP chemistry. And it's been different examples throughout the years, but guys, every year since then, we've had to get up here and we've had to talk about how to balance oxidation reduction reactions. And so I have worked examples in front of students for 18 years. 2 years ago is the first and only year where I've done 2 of these without making a mistake. And you know how sometimes I try to make mistakes to point out the mistakes you're going to make? Guys, full on, I'm trying to do these right, but you're going to see the details are so wacky crazy when you're balancing oxidation reduction reactions that I've only got this right once in 18 years. So let's shoot for 2, and this will be 2. Well, 1 in 17. Hopefully this is 2 in 18. All right, so here we go, guys. Background information. Bottom line, guys, this is it. This is what we're doing for this entire unit. We are chasing electrons. When oxidation reduction reactions take place, electrons are being exchanged. Now, guys, here's the problem. We can't see electrons, right? So what is it that we see that gives us evidence that electrons are moving around? Exactly. What we're going to see is charges change. And guys, those charges are technically what are called oxidation numbers, but that makes sense because we're talking about redox chemistry. So the trick here is that as electrons are moving, what we're actually seeing is charges change. So how does this work? Well, guys, this is where we start talking about terminology. When electrons are transferred, electrons are moving from the atom that is oxidized to the atom that is reduced. So guys, fundamentally, what does that mean? Well, that means that oxidation is the loss of electrons and reduction is the gaining of electrons. That's it, and that's where the name comes from. Right. So guys, get it in your notes, and then I'd like to talk with you about where these names come from, whatever. And then we'll talk about how to memorize or maybe some things that you can keep track of that'll make this more straightforward. But guys, this is the point where you need to start adopting some strategies that allow you to remember this stuff. So guys, fundamentally the idea is this. Oxidation means to lose electrons, reduction means to gain electrons. So guys, why on earth in the 1800s did they decide to call the loss of electrons oxidation? Say it again. Guys, that's the trick. So when they first started studying oxidation, the things that they were studying were metals that were oxidizing. And guys, what do we call oxidized metals? Rust. They were literally watching metals oxidize, and what they found is that when metals oxidized, they were losing electrons to oxygen, and so they said oxygen is stealing electrons, causing those metals to lose electrons, and because oxygen was the cause of it, they called it oxidation. And then Jake was actually onto the other idea. Why do they call gaining electrons reduction? And of course, the idea is that when you gain electrons, your charge goes down because they're negative. So reduction is the loss of electrons causing a reduction in charge. Is that good? Or sorry, gain of electrons causing a reduction in charge. You good? Okay, so guys, this is how I remember it. I like to remember the idea that the charge of the atom that is reduced is reduced. That's my starting point. I go back to that at the beginning of every year. frankly, very quickly, I can just picture the idea that reduction is gaining electrons. But guys, I know that there's another competing strategy for this that apparently they teach up at the U. Did they, Talmadge, teach you the oil rig trick? Did they? Okay, so I don't even think it's in my notes. But guys, apparently up at the U, from those that have gone to the Summer Institute, apparently they like to talk at the U about oil rig, O-I-L-R-I-G. Oxidation is loss, reduction is gain. Oil. Yeah, I know, but there you go. Up to you, however you want to do this. But guys, in any case, in any oxidation reduction reaction, guys, you got to understand both have got to occur. You can't have oxidation without reduction or reduction without oxidation, because you can't lose electrons without anywhere for them to go, and you can't gain electrons without a source. So guys, now we need to talk about the idea of agency. This is new. This is going to be Friday. This gets confusing, but I want to lay this on you right now, so if you want to scratch it into your notes, because we're not going to do anything more with the idea of agency yet. We will on Friday, but I wanted to introduce it to you now. So guys, when we talk about oxidation and reduction, we understand oxidation is the losing and reduction is the gaining of electrons. But we can also change our focus and we can talk about agency. So if we talk about an oxidizing agent, when we say agent, we're talking about what it does to the other guy. So if you are an oxidizing agent, you're causing oxidation in the other guy. So if the other guy is being oxidized, he's losing electrons. So the oxidizing agent, as it causes oxidation in the other, is actually being reduced. Does that make sense? And then guys, similarly, when we talk about reducing agents, a reducing agent is causing reduction in something else. So the something else is being reduced, gaining electrons. So that means the reduction agent, which is causing reduction in the other guy, has to lose electrons to cause the other guy to be reduced. That means the reducing agent is oxidized. So it's opposite, because we're talking about what's happening in the other guy. So, guys, if that didn't make a ton of sense yet, frankly, it's because you are not yet fluent in the language of oxidation and reduction. For now, just understand that agents refer to what they do to the other guy. The oxidizing agent makes the other guy be oxidized. The other guy lose electrons, so that agent is reduced. Similarly, the reducing agent causes the other guy to be reduced, so that guy is oxidized because it's losing electrons, causing reduction in the other thing. So guys, just understand the idea of agency is what they're doing to the other guy. Understand that the oxidizing agent is reduced, the reduction agent is oxidized, and we're going to talk all day about that on Friday. Mind-blowing? You notice how fluent I am in this stuff? It just rolls off the tongue. You guys good? You're good? All right. So again, guys, if that was like, whoa, by Friday, you're going to be much more conversant in this, and it'll go much better. I just wanted to introduce the idea to you now. Okay, so guys, with that said, we need to go on and talk a little bit more about background. Please don't write any of this down. Trust me on that. Here's the deal. So guys, in general, relative to oxidation reduction reactions, first of all, they tend to be spontaneous. These things happen. Doesn't mean they happen fast, right? Rusting takes a long time, but oxidation reduction reactions tend to be spontaneous, which is of course encouraged by the fact that they tend to be exothermic. And you guys know that, right? When a nail rusts, it gives off heat. You guys know that? When a nail rusts, it gives off heat. Guys, but it happens so slowly that it doesn't give off enough heat that you notice it. Until you grind up the iron, put it in the presence of an element that's got a lot more oxygen in it, and then wrap it up in a little plastic bundle, and then guess what you've got? A heat pack. You know those heat packs that you can buy by the box at Walmart and you shove them in your gloves when you're up skiing? Guys, that's all that's going on inside there is iron is rusting. It's just that the iron is ground up into a really fine powder. Why does that speed up the reaction? Surface area, and they've got a source of oxygen in there that just dumps electrons into, well, dumps oxygen into it's just rusting like crazy, and as it does, it gives off heat, and that's what warms up your hands. Huh, All right. So, guys, additionally, what we're going to find out, and this is what we're going to do on Wednesday, is that because oxidation reduction is an exchange of electrons, what we can actually do is we can take the thing that's being oxidized, losing electrons, take the thing that's being reduced, gaining electrons, separate them, hook them up with a wire, and we just made a battery. Guys, that's all a battery is an oxidation and a reduction happening in separate compartments. And if you can force the exchange of electrons to not happen through space but through a wire, then you've got a battery. And that's what we're going to talk about on Wednesday. So guys, all of this leads up to a couple more thoughts. First of all, if a redox reaction is not spontaneous, you can actually force them to happen by applying a current. This is what a battery charger does. Think about that. Guys, oxidation reduction reactions are batteries, and they have a spontaneous direction, right? And as they happen, this current flows, and then if we want them to go in the non-spontaneous direction, we know that reactions can be forced in their non-spontaneous direction by doing work on them, and that's what battery chargers do. A battery charger actually forces a redox reaction to go in its non-spontaneous direction, and that resets the battery. So guys, we're going to talk about all of this stuff as we talk about things like batteries, electroplating, and the corrosion of metals. Good summary, good overview. Here we go. Guys, this is about to get real. So what we need to do now is we need to start talking about oxidation reduction and applying these terms to real life situations. So guys, scratch this down with me. Put this in your notes. This is the reaction between zinc and hydrochloric acid. It's obviously a single displacement reaction. Some of you may remember it from last year because this was the reaction where you dropped the zinc into the hydrochloric acid, you inverted a test tube over the top of it, gathered the hydrogen gas, shoved a lit popsicle stick in there, and it went boop, and y'all got excited and chuckled. That would be this reaction. You may have giggled, some chuckled, others giggled. So guys, here's what I want you to do. And all the answers are in the notes, so we've just got to talk about this conversationally. What I want you to do is identify the substance in this reaction that's being oxidized. Identify the substance in this reaction that's being reduced. And then beneath those substances, write that down. In addition to that, guys, I want you to identify how many electrons are being exchanged in this process. Now, guys, in order to do that, what we need to do, wait for it. In order to do that, guys, what we need to do is we need to successfully identify charges. And maybe that caught you off guard. And so consequently, I can maybe help you with that a little bit. Okay. So guys, let me tee this up for you. Because we said on the previous slides that we can't see electrons move, so what we look for is charge changes. So let's assign some charges. Off the periodic table, zinc is +2, hydrogen's +1, chlorine's -1. Then guys, we've got +2. Oh, no, I'm sorry. No, I'm sorry. Yeah, my bad. Sorry, hold on. In its elemental form, zinc is 0. +1, -1, +2, -1, and 0. Guys, remember the idea that atoms in their elemental forms are understood to have no charge. It's not until zinc reacts with the chlorine that it takes on a charge. We'll talk more about that in a minute, but these are their charges. But again, guys, elements in their elemental form, whether it's diatomic like H2 or zinc on its own, they're understood to have oxidation numbers of 0. So again, guys, the idea is which is being oxidized, which is being reduced, how many electrons are being exchanged. Give you another second. And then we'll talk. You guys okay? So guys, what are we looking for when we figure out who's being oxidized and reduced? Charge changes. So let's do this first. Whose charge is not changing? Chlorine. So guys, what does that make chlorine? A spectator. We haven't made that connection yet, but guys, if we were writing the net ionic equation, chloride is an ion in solution in the left, chloride is an ion in solution in the right. Chloride does not change charge. We could have previously identified it as a spectator, but now we know why. So now let's look at who's changing charge. So guys, notice that zinc goes from 0 to +2. I was going to ask you if that means oxidized or reduced, but I don't know that many of you are there yet. So let's do this in increments. Guys, is zinc gaining or losing electrons? I'm glad we did it in steps. Guys, zinc is going from 0 to +2. Be careful, guys. Zinc is going from 0 to +2. So what is zinc doing? Losing electrons. So if this loses electrons, zinc is being oxidized. So guys, be very careful. Hear this carefully. If zinc is being oxidized, what's being reduced? Let's look. So hydrogen is going from +1 to 0. Can you see the charge going down from +1 to 0? So what is being reduced? What is being reduced? No. What substance is being reduced? It's not hydrogen. It's hydrogen ion. Guys, that's important. Hydrogen is not being reduced. This is hydrogen. Hydrogen is a gas. That is not being reduced. The thing that is being reduced is hydrogen ion. Some of you are thinking, wait, that is subtle and maybe nitpicky. If that's what you're thinking, it's because you don't understand. Guys, hydrogen ion and hydrogen are not the same things. If you don't believe me, hydrogen ion is a proton. Hydrogen atom is two of these bonded together as a molecule. Hydrogen ion and hydrogen have nothing to do with each other than their name, and they both contain one proton. So guys, understand it's hydrogen ion that is being reduced to hydrogen. If you wrote on the AP test, if the question said, what is being reduced, and you wrote hydrogen, that's wrong, because it's wrong. So guys, you got to understand the difference. Now, how many electrons is zinc losing? 2, right? It's going from +2 or 0 to +2. So this is losing 2 electrons. Now guys, how many electrons is each hydrogen ion gaining? 1. Do you see how this works out though? There's 2 of them. So guys, the idea here is that each hydrogen ion is gaining 1 electron for a total of 2. And guys, those have always got to balance. The electrons that are being lost by the substance that's oxidized has always got to equal the electrons that are gained by the thing being reduced. You okay with the ideas? Yeah. You guys good? They would use the term species. What is the species? That's, yeah. You guys good? All right. Yes, absolutely. Oh yeah, but yes, H plus is being reduced is just fine. Yeah, definitely. Okay, so guys, with that said then, we now need to talk about where this is headed. So guys, here's the scoop. We are now for the rest of this day going to talk about balancing redox reactions. So guys, this is largely conversational. I don't know that you need to write this down, but it's about to become very practical. So guys, up until now, when we've balanced equations, the only thing that we've done is tried to obey the law of conservation of mass. all of the atoms that go in have got to equal all the atoms that come out. Well, guys, it turns out that in redox reactions, we must also balance the number of electrons. As we saw in the other example, the one that we just did, the number of electrons have got to balance. And it's nice that they did. Zinc lost 2 electrons, 2 hydrogen ions each gained 1, and we had a balance in electron exchange. Well, guys, seldom is that the case. And that's what makes these so bloody ridiculous to balance. It's crazy. So guys, what I want to do to help you be successful with this poor thing, my clicker. I don't know if I have replacement batteries. That's okay. Guys, to help you be successful with this, here's the steps. Yep. Here's how you balance redox reactions. What? I think so. I think you will find this in the book. Yep, and that's the first thing we need to, it's the next thing we need to talk about. So guys, the steps go like this. Step number 1 is to balance the half reactions. You don't know what that means yet. We'll show you in a minute. Then guys, once you've got your half reactions identified, you will then simultaneously balance each of these half reactions. But you have to balance them in this order. The first thing that you do is balance all the other elements except for hydrogen and oxygen. Then you balance the oxygens by adding water. Then you balance the hydrogens by adding protons. Then you balance the electrons by adding electrons to the sides of the half reactions that causes the charges to balance. Then guys, you multiply one of the 2 half reactions by the multiplier that's necessary to make the number of electrons on both half reactions equal. Then you add the 2 half reactions together and simplify. Then if the equation that you're balancing, if the reaction that you're balancing happens to be in a basic environment, you will then get rid of any excess protons by adding sufficient hydroxides to convert them to water. Got it? Mm-hmm. So guys, the process thing goes like this. I need to teach you what half reactions are. Then once we've got that, we're going to balance 2 of these. And then you're going to have probably not a lot of time to work on homework. You guys all caught up? How about now? Hey.
So on some of your equations, your random charge, you have 2 plus, and plus 2.
Yeah, so here's the thing. It actually does matter. That charges are number and then sign. Oxidation numbers, which are an indication of how many electrons atoms share when they form molecules, should be charge and then number. They don't care on the AP test. In college, half my professors did care, half my professors didn't care. So there is a difference. That if you go 2 plus, that's a charge. If you go plus 2, it's an oxidation number. But you don't need to worry about it for AP. Okay, guys, so let's go back. Do you like the last 2? Yeah. All right, here we go. So guys, half reactions go like this. Please don't write any of this down. Just trust me and watch. So guys, this is the reaction that we just talked about. And remember what we identified previously. We said that zinc is being what? Oxidized or reduced? Oxidized, losing electrons. We said that hydrogen ion is being reduced. Now, we also identified, guys, that there were 2 electrons moving around. Now let's turn these into half reactions. So guys, what is a half reaction? What half reactions do, Matt, focus. What half reactions do is they allow you to identify the oxidation and the reduction separately. The thing that makes these different is that they are never subtractive. It's always plus electrons. So guys, let me show you what that means. So let's do our reduction half reaction first, because reduction is the gaining of electrons. So guys, how did that reduction go? Well, what we had was 2 hydrogen ions gaining 2 electrons, and that formed H2. So guys, that is the half reaction that represents the reduction. Now let's look at the oxidation, because this is interesting. So guys, we understand that it's zinc that's being oxidized, right? But guys, check this out. When we write the oxidation, we do not write zinc minus electrons. Yes, the zinc did lose electrons, but we don't represent it that way. Instead of representing this zinc minus electrons, what we do is we go zinc ion plus electrons. So it's always additive with the electrons. So what does that then tell us? Well, guys, notice where the electrons are here. They're on the reactant side. That will always be the case for the reduction half reaction. So in a reduction half reaction, the electrons are always a reactant. And then, guys, in the oxidation half reaction, the electrons are always a product. Oh, yes, sorry. Thanks. You get the idea. You guys, and we could. But the idea here is you understand, guys, that our half reactions allow us to represent both reactions. The reduction, you will always have electrons as a reactant, and in the oxidation, the electrons are a product.
And those half steps, we're always using reduction, oxidation. Nothing else. It's just 2 sub-steps which show the reduction and the oxidation.
Because that's what oxidation reduction reactions are made of. Yeah. Yep. You guys good? Okay. Here we go. Oh boy. Guys, we're going to balance this reaction. This is usually the one that screws me up. So guys, here we go. Those steps that I gave you, we are now going to apply in this environment. So here we go. So guys, step number 1 is kind of find the middle of your paper. And you're going to need about 10 lines to do this. So what I like to do is I like to separate my page in half and literally put a little tick mark there. You have the advantage of having lined paper. I don't get that. So now, guys, and here's the rule. It's just like playing chess. It doesn't count till I take my hand off the paper, so to speak. So, guys, I get to go back and make changes. We'll see if I can do this right. So we need half reactions. So guys, the half reaction goes like this. I minus is becoming I3 minus. There is one of our half reactions. Center it in the left half of the page. That's close enough. Then, guys, our other half reaction is IO3 minus yields I3 minus. You'll notice that we've got two reactants forming one product. As a result, both of our half reactions have to go to the same product. So now, guys, we dig into this process. First thing we need to do is balance all of the elements other than oxygen. So in this left side half reaction, we've got 1 iodine on the left and 3 on the right. So we need to go 3 I minus yields I3 minus. Now, guys, you'll notice that similarly here, we've got 1 and 3 iodines. So we've got 3 IO3 minus yields I3 minus. Well, I haven't screwed up yet. Now, guys, we get into the more complicated balancing. We need to balance oxygens. Just trust me on this. There's no oxygens right here. Rewrite it. You want to do these in lockstep. So, guys, 3 I minus yields I3 minus. And now, guys, we do have oxygens on the left-hand or right-hand equation. And so we balance those by adding waters. So how many oxygens do we have on this guy? 9, right? So what we need to do then is we need to go 3 IO3 minuses yields I3 minus plus 9 water molecules. Did I screw that up? Oh, good. Okay. Now, guys, the next balancing step is to balance hydrogens by adding protons. Notice we still don't have any on the left, but I'm going to carry this down to keep these in lockstep. Now, guys, you'll notice that on our right side half reaction, we've got 18 hydrogens. So now we need to go 18H plus 3 IO3 minus yields I3 minus plus 9 waters. You can do whatever you want. Okay, now, guys, we've got to balance charges. I'm going to switch colors. This is where these things tend to crumble at your feet. Because, guys, if you simply leave off one little negative sign, you get the charges all wrong and these will never balance. So if you get to this point and you're finding that you're getting in trouble, go back and make sure you've got all your signs right. And remember, water doesn't have a charge. Okay, so now we need to balance charges by adding electrons to the side that is more positive, because negative electrons will cancel positive charges. So, guys, what is the total charge on the left-hand side of the left-hand half reaction? -3. So, guys, what is the total negative charge on the right-hand side? -1. I'll even write that out as -1. So now, guys, the only thing that we have at our disposal is to add electrons, and we need those charges to balance. So, how do we make -1 as negative as -3? Add 2 electrons. So this then becomes 3 I minus yields I3 minus plus 2 electrons. Now the charges balance at -3. Do you see that? Okay, now, guys, similar thought over here on the right. This doesn't count as a mistake if I get this wrong. The positive charge on the left, I get plus 15. And then over here, minus 1. Do you buy that? All right, water doesn't have a charge. Protons are 1 each. Those 3 IO3s are minus 3. Is that right? Okay, so now, only being able to add electrons, how do we make the charges balance? Add 16 electrons to the left. So we've got 16 electrons plus 18 protons plus 3 IO3 minuses yields I3 minus plus 9 waters. My pen's still on the board. I think I'm okay. Am I okay? Okay, now guys, I would encourage you to make not a mental note. You're going to want to write this down. This is a good place, just hear this out and then you'll understand what to write down. This is a good place to make a check. So guys, check this out. Here we have the electrons on the product side. See? Oxidation or reduction? Oxidation. This, when electrons are a product, that's an oxidation. So we now know that this is our oxidation side. If this is the oxidation, the other one's got to be reduction. So where do the electrons have to be? The reactant side, and sure enough they are. So guys, this is a good place to make a check. I'll just sort of write in a double-headed arrow as my reminder, but it even points at the electrons. That's handy. Guys, you've got to make sure at this point that you've got one side where electrons are a product. It could be the other sides, but you've got to have them as a product and a reactant. What if you've got electrons and they're both products or both reactants? You screwed up. That can't be. Oxidation can't pair with oxidation or reduction with reduction. So you've got to have them on the same sides. Okay, now guys, moving along, what is our next step? We are going to multiply we're going to use a multiplier to make the number of electrons equal, because the number of electrons lost and gained have got to be the same. So can we all see that we're going to multiply the left-hand half reaction by 8? Okay, so here we go. So we're going to go 24 I minus yields 8I3 minus plus 16 electrons. Now guys, here's the thing. At this point, I think that this is a safe time to allow these to fall out of step. I don't think it's necessary to rewrite that half reaction. The reason is this. It's now time to add these up. So we're going to take the reactant sides of both 24 I minus plus 6 plus 16 electrons plus 18 hydrogen ions plus 3 IO3 minuses yields 8 I3 minuses, 16 electrons, 1 I3 minus, and 9 waters. Pen still on the board. I think I'm okay. We okay? So now guys, at this point, we cancel things that'll reduce. Obviously, our 16 electrons go. If they didn't, we screwed up. There's no iodines. Right. So guys, in total then, we get 24 I minuses plus 18 protons plus 3 IO3s yields 9 I3 minuses and 9 molecules of water. What? Oh, crap! Oh! Yes, not only can you, you have to. Guys, you have to divide then by 3. So it would be 8, 9, 1, 3, and 3.
Oh, you didn't take it down.
No, I did. I told you. And the thing is, you'd get the whole thing wrong.
That counts as a 1 5.
No, I mean on the AP test. Oh, good. Okay. All right. So, guys, but do you understand? And I'm not going to do it, but you do need to divide by 3 because equations always balance in simplest terms. I really thought this was my year. So funny. All right. What do you think? You guys okay? Okay, so now, guys, we're going to do one more. Okay, so guys, we're going to go through these maybe a little more rapidly. You've seen the process, but here's what you're going to see. The beginning and the end change. The beginning changes because now we need to pick what our half reactions are. Previously, we only had one product, so both of our half reactions resulted in the same product. Now that's not the case. So here's what you do. Match up elements. So this is Cu2 plus yields Cu. This is N2H4 yields N2. Now, guys, the other thing that you're going to notice is that this is now in a basic environment. Don't worry about it now. It changes the end. So, guys, you ready? Step number 1, write your half reactions. Done. Step number 2, balance the elements other than hydrogen and oxygen. Done. Step number 3, balance, do we do oxygens next? Balance the oxygens by adding water. Done. Step number 4, balance the hydrogens by adding protons. That we need to do. So we've got Cu2 plus yields Cu. Then we go N2H4 yields N2 and 4 protons. So now, guys, we've got to balance the charges by adding electrons. This side's +2, that side's 0. So this will be Cu2 plus 2 electrons yields Cu. And then, guys, here we've just got that +4 charge on the right. So we've got N2H4 yields N2 plus 4 protons plus 4 electrons. You good there? Now we need to do the multiplier that makes these equal in terms of electrons. So we've got 2 Cu2 plus 4 electrons yields 2 Cus. Now, guys, at this point, we can bring them together. So we've got 2 Cu2 plus 4 electrons plus N2H4 yields 2, bless you, Cus plus N2 plus 4 protons plus 4 electrons. Now, getting rid of things, our electrons go, and that's it. So we get 2 Cu 2 plus N2H4 yields 2 Cus plus an N2 plus 4 protons. You guys okay? We're not done, but are you okay? Okay. Now guys, here's the trick. If this reaction was happening in an acidic environment, we'd be done, because an excess of protons indicates an acidic environment. But because this is in a basic environment, we don't have an abundance of hydrogen, we have an abundance of hydroxide. So what we do is we look at our abundance of hydrogen, there's 4, and we add that same number of hydroxides. Oops, that doesn't count, I just ran out of space. So we are going to add 4 hydroxides here, and then similarly, we're going to add 4 hydroxides to both sides. This then results in our complete equation. So we've got 4 hydroxides plus 2 copper ions plus N2H4 yields 2 coppers, an N2, and now guys, look at what happens. 4 waters. So that's how to deal with basic environment. Guys, one other thing that we forgot to mention, because we were kind of skipping through this, but it is worth mentioning. When we got to this point, when we added electrons, it really is a good idea to make sure that you've got electrons as a reactant and a product so that you don't move on and just work yourself into a hole. So that's how that balances. You guys good? Okay, so here are some for you to play with. Here's your homework.